Hi, I'm Bob. Welcome back to 5 Minute Econometrics. In the previous topic, we learned how to detect whether the model exhibits heteroskedasticity. That is, whether the error term of the model has a non-constant variance. If heteroskedasticity is of an unknown form, we can use the heteroskedasticity robust standard error to form the t-statistics and estimate intervals. Today, we will explore the case when we know the specific heteroskedasticity form of the error variance. In that case, we can apply the weighted least squares WLS method to the data and obtain estimates that have smaller variance than the ordinary least squares OLS method. In other words, we can find a consistent and efficient estimate if we know the structure of the error variance. Suppose the original model contains one explanatory variable x. The variance of the error term equals sigma square times x. It means the error variance increases with the explanatory variable. It occurs in many models, such as those using education to explain hourly wages. Workers with more years of education may have a more spread distribution of hourly wages. As we plot hourly wages against years of schooling, we find that the hourly wage has a larger variance for workers who have more years of schooling. It implies that the error variance increases with the explanatory variable in the model. The usual OLS estimate is no longer the most efficient estimate, and the standard error, t-statistic, and f-statistic are not valid in the presence of heteroskedasticity. The idea of the weighted least squares WLS estimation method is that we construct a new error term that has a constant variance, so that we can apply the OLS method on the transformed model. It requires us to know the specific form of the error term. Suppose the error term equals sigma square times x. The transformed model looks like this. All terms are divided by the square root of x. So the variance of the transformed error term is a constant, sigma square. We regress the transformed outcome variable, y star, on the transformed intercept, x0 star, and the transformed explanatory variable, x1 star, using OLS without an intercept. We obtain the weighted least squares estimates. They are consistent estimates of the population parameters and have the smallest variance. Let us examine the general case where the error variance equals a constant sigma square times a function of x, hx. The error variance for each observation is not the same. It changes with the explanatory variable x. That is why we use a subscript I to emphasize that the error variance is individual specific. For this multiplicative form of heteroskedasticity, the weight we should use is 1 divided by the square root of hx. When all elements of the original model are multiplied by this weight, we have the transformed model. It can be proved that The error term in the transformed model has a constant variance, sigma square. The coefficients in the original model, beta 0 and beta 1, are preserved in the transformed model. What we need to do is to construct the transformed variables and run an WLS regression without an intercept. Next, we will use simulated data to perform the weighted least squares estimation in Stata. We will verify that the standard error for the WLS estimate could be smaller than the OLS estimate. Suppose the population model is y equals phi plus 2 times x plus mu. I set the error term mu with a zero mean and a standard deviation of x. In this way, the error variance equals squared x, and it increases with x. The h function is x squared. According to what we just derived, the weight equals 1 divided by the square root of the h function. It is 1 divided by x in this case. With the weight in hand, we transform the outcome variable, the explanatory variables, and the error term in the original model. The error term in the transformed model has a constant variance that equals 1. In Stata, we begin by setting the number of observations. Next, we generate the explanatory variable, which follows a random uniform distribution. A key part of this setup is the error term, denoted as mu. This error term is defined as a standard normal variable multiplied by the explanatory variable x. As a result, the variance of mu is equal to x squared. Next, we generate the outcome variable y based on the population equation. We can find the pattern of the heteroskedasticity when we scatter y against x. Now we have data that exhibit heteroskedasticity. We can compare the OLS and the WLS estimates and see which one is better. Both the WLS and the OLS estimates are very close to the population parameters we set. They are both consistent estimates. However, the WLS estimates have smaller variances or standard errors than the OLS estimates. For example, the standard error for the slope estimate is 0.017 in the weighted least squares estimation, but 0.024 in the ordinary least squares estimation. We use the hourly wage example to illustrate that the weighted least squares method could lead to smaller standard errors of the estimates than the ordinary least squares method. The model relates workers' hourly wages to their years of education. After WLS estimation, we can use the residual versus fitted plot command to find the pattern of the residuals. It exhibits heteroskedasticity. In addition to transforming variables manually, Stata provides the weight option when we run a regression. The standard errors of the weighted least squares estimate are smaller than those of the ordinary least squares. Finally, I include the heteroskedasticity robust standard errors as a comparison. Today, we explored the weighted least squares WLS estimation, which is used when we are aware of the structure of the error variance. By knowing the form of heteroskedasticity, we can create the transformed variables using weights and estimate the transformed model by WLS to obtain the WLS estimates. The weighted least squares estimates are consistent and efficient estimates of the population parameters. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.